This is Li Wei, the course instructor of ENGR 350. So in Module 1, we learned how to solve a second-order circuit. In this example, I want to show you a general RLC circuit and how do we solve this general RLC circuit. So let's look at the example. So assume I have the following circuit, which is second order circuit. So in the circuit I have a current source. So the current source has 4 U of t amp. So later on I will explain what is U of t means. So we have a resistor 4 ohm. So we have a capacitor 1/4 farad, and we have a inductor 1 Henry, and we have another resistor 6 ohm. So we can define the inductor voltage plus minus VL. So the inductor current is defined according to the positive convention. That means the current flows from the positive terminal of the inductor to the negative terminal of the inductor. So it is IL. So this is according to positive convention. So let's define the capacitor voltage. So if I assume the capacitor voltage is plus minus Vc, so according to positive convention, the capacitor current is defined it flows from the positive terminal to the negative terminal of the inductor of the capacitor. So IC. So also I define the resistor current I and the another resistor voltage V. So what I'm going to solve is to obtain I of t and V of t for t is larger than 0. So we know that U of t is a unit step function. So basically U of t means, so if I have time axis, I have U of t. So this is time 0. So when time is less than 0, so U function is 0. So when time is larger than 0, U function is 1. So this is a so-called unit step function. So basically U function is a two-value function. So U of t is equal to, so when t is less than 0, it is equal to 0. So when t is larger than 0, it is equal to 1. So this is equivalent to a switch operation. Okay, so let's see how do we solve this second order circuit. It is second order circuit because we have two energy storage components. One is the inductor, another one is a capacitor, another one is the inductor. So let's look at the first step. So we introduced in the lecture. So for the first step, so we should solve for the initial conditions. So at t is equal to 0 minus, or when t is less than time 0, at t is equal to 0 minus, because the current source is 0. So the inductor current IL 0 minus is 0, and the capacitor voltage Vc 0 minus is also 0. So there's no initial charge because the source is 0 when t is less than 0. So the second step, at t is equal to 0 plus, when time is at a post 0 time. So the inductor current at post 0 time is equal to the inductor current at pre-zero time, because the inductor current is always continuous, so it is 0. So the voltage Vc 0 plus is equal to Vc 0 minus, because the capacitor voltage is also always continuous, so it is 0. So the third step, so when t is larger than 0, in the third step we find out the transient response of the circuit. So let's redraw the circuit diagram again. So we have a current source. So when t is larger than 0, so the current source, we have 4 amp. We have the resistance 4 ohm. So we have the capacitance 1/4 farad. We have the inductor here 1 Henry. So plus minus VL. The current is IL. So for the capacitor is plus minus Vc. So the capacitor current, according to positive convention, it is IC. And we have the resistor 6 ohm. So I'm looking for V when t is larger than 0, and I'm looking for I when t is larger than 0. Okay, so let's find the transient response. So in this step, what I need to do is find the natural response. So that means I should turn off my independent sources. So I turn off the independent sources. In our case, this is a current source. We should turn off the current source. That means we should open circuit our current source to turn it off. So if we have a voltage source, plus minus, if we have voltage source in the circuit, so if we want to turn off this voltage source, so we should short circuit it. So if we have a current source, if we want to turn off the current source, so the current will be 0. So that means we should open circuit it. So in our case, it's a current source. So we should make the current source open circuit. We turn off the current source to find the natural response of our circuit. So the natural response of our circuit give us the transient response changing mode. So it's corresponding to the homogeneous solution of our second order differential equation. So let me draw it. So it's 1 Henry plus minus VL IL plus minus VC IC, and the resistor here is 4 ohm. The current source is open circuit, so I don't draw it, and I have 6 ohm. So I'm looking for so look at this circuit. So this circuit is neither series nor parallel RLC circuit. It's neither series nor parallel RLC circuit. So we cannot use, alpha and omega 0 that we learned for parallel or series RLC circuit. So we have to build up a differential equation. So let's formulate a second order differential equation, ordinary differential equation. So let's first apply KCL at node A. So node A, if I define node A is here, so the current flowing through the 4 ohm resistor is I, so this is I. So I plus IC plus IL is equal to 0. So we know that the 4 ohm resistor, the voltage applied to the 4 ohm resistor is equal to VC because they are connected in parallel. So that means VC over 4 is equal to I plus IC. So the capacitor current is equal to C dVC over dt. So it is 1 over 4 farad, 0.25 dVC over dt plus IL is the inductor current. IL is 0. So we have this differential equation. So let's massage the equation a little bit. So we times 4 to both sides of the equation. So we have VC plus dVC over dt plus 4 times IL is equal to 0. So we have two variables, VC and IL, in the equation. So we want to replace one variable with another variable. So here, say I want to replace VC using IL. So how do we do that? So let's look at our circuit. So in our circuit, so we have VC here. So we can use KVL to find out. So here VC, if we look at this loop, so if I use KVL, so VC voltage is equal to VL voltage plus the resistor voltage, 6 ohm resistor voltage, V. So VL voltage is equal to L DIL over dt plus the resistor voltage. So it is 6 ohm times IL. So we can calculate dVC over dt based on this equation. So it will be, so L is 1 Henry, so DIL second derivative with respect to t plus 6 DIL over dt. Okay, so let's look at our original differential equation. So VC, let's replace it with IL using this equation. So we have L is 1 Henry, so it is DIL over dt plus 6 times IL plus dVC over dt is equal to DIL second derivative of t plus 6 DIL over dt plus 4IL is 0. So let's combine the terms. So what we have here is DIL second derivative plus, so we have 1 DIL over dt plus 6 DIL over dt, so we have 7 DIL over dt plus 6 plus 4 is 10 IL is 0. So this gives us the homogeneous solution of our second order circuit. So we need to find out the characteristic equation of this second order ODE. So the characteristic equation is very easy. So we replace DIL over dt by S. So S squared plus 7S plus 10 is equal to 0. So what we have here, so we can solve for s. So we have s plus 2, s plus 5 is equal to 0. So we can solve for s1 is equal to minus 2, s2 is equal to minus 5. So we have two real non-identical roots. So we can find out the transient response, which is the general solution for the homogeneous second-order differential equation. So the current IL, the transient current IL, has the following form. So you have A1 times E S1t plus A2 times E S2t. So A1 and A2 are integration constant that we have to solve, using initial condition later on. So I can substitute S1 and S2 into the general solution form. So I have A1 times E minus 2t plus A2E minus 5t. So this is the transient response. So this transient response will die out when time is sufficiently large. So the first step is when t is sufficiently large. So what is the steady state response? So let's find out the steady state response of the inductor current IL. So first let's look at how the circuit look like if time goes by for a long time and if the circuit is in steady state again. So how the inductor current look like. So because here we have the 4 amp current source, so in steady state, so this current source will flow through the inductor. So for the inductor in steady state, because it is DC, so because DC current flows through it, so the inductor is a short circuit. And for the capacitor, because it's a DC circuit, the capacitor will be open circuit. So we can replace the inductor with a short circuit and the capacitor with open circuit. So let's draw the circuit again. So let's copy the circuit again. So I have 4 amp current source, and I have resistor here, 4 ohm. So this is the current I flowing through the resistor, and I have a capacitor here, 1/4 farad, and the voltage is VC. The current flows through the capacitor is IC, and I have a inductor. The inductor voltage is VL, the current is IL, and I have another resistor, 6 ohm resistor. The voltage is V, and because I was solving for IL for transient response, now I want to find out IL for steady state response. That means when the circuit, when the time goes by, the circuit come to steady state again. So what is the steady state current IL? So we know for an inductor, if the circuit is in steady state, it's a DC circuit, so the inductor current is constant. So that means the inductor will be equivalent to a short circuit. For the capacitor, because it is a DC steady state, so the capacitor voltage is constant. So that means C dVc over dt is equal to IC, because V is constant, so the capacitor current is 0. So we can use open circuit to replace the capacitor. So let's simplify our circuit again. So I have my current source, 4 amp. So I have the resistor 4 ohm. So my capacitor is replaced by open circuit because it's a DC steady state, and my inductor is replaced by a short circuit. So here I have 6 ohm resistor. So what is the steady state inductor current? Okay, so for this IL SS, because we know here the 4 ohm resistor is in parallel with the 6 ohm resistor, so the total current is 4 amp. So according to current divider, because the total current is 4 amp, so the current flowing through one parallel branch, which is 6 ohm, is equal to 4 amp times. So we have a formula, the so-called current divider. So for the denominator, so it is the sum of the two resistance in the two parallel branch. And for the numerator, so it is the resistance value in another branch. So it is 4. So this is the so-called current divider. So it tells us the current is equal to 4 over 10. So it is 1.6 amp. So current divider is a very important concept. If you are not very familiar with the current divider, so we can also use another way to calculate the current flow through the 6 ohm resistor. So first we can calculate VR. So we know the total current is 4 amp. So how much is the total resistance for the parallel branch, 4 ohm and 6 ohm parallel branch, the total resistance? So it is, the total resistance is 4 plus 6 for the denominator. For the numerator is 4 times 6. So this is the total resistance. So the total current times the total resistance give us the wattage across the parallel branches. So it is 4 times 24 divided by 10 volt. So if we know the total wattage here, VR, so the current ILSS, the steady state current, so it is equal to the wattage VR divided by 6 ohm. So it is 4 times 24 divided by 10 divided by 6, so give us the same result. So it is 1.6 amp. So we know the steady state inductor current is 1.6 amp. So step 5, so we can calculate the total inductor current, the total solution. So the total solution, or the total inductor current, has two components. One is the transient response. So this response is this. So this response will die out when time goes by. So the another component is the steady state response. So for ILT, so we know the transient response form. So it is this. So we have A1E minus S1T. So S1 is minus 2T plus A2E minus 5T plus the steady state response of the inductor current IL is 1.6 amp. So now, so we need to find out the integration constant A1 and A2. So we have to use initial conditions to find out A1 and A2. So for the second order circuit, we have two initial conditions, which is the inductor current and the capacitor voltage at 0 plus time. So if this solution is the time domain response when t is larger than 0, that means IL 0 plus, if I substitute t using 0 plus, so it should give me the current response at post 0 time. So it is A1 times, so e to the power of 0 is 1 plus A2 times e to the power of 0 is 1 plus 1.6. So from initial condition, I know IL 0 plus is, we can find out from the initial condition. So it is 0. So this must be 0. So because if this is the solution, so the solution must satisfy the initial condition. So here we have two integration constant A1 and A2. So we need to find the second equation to solve for A1 and A2. So the second equation comes from the second initial condition, which is the capacitor voltage. So but how do we relate the capacitor voltage with the inductor current form? So we can do the following. In order to find out the second equation to solve for A1 and A2, so we can take the first derivative of IL with respect to t. So let's look at here. We know the IL formulation, so let's take the first derivative. So it is equal to A1 times minus 2 times e to the power of minus 2 plus A2 times minus 5 times e to the power of minus 5 plus 0. 1.6 take the derivative is 0. So if this equation is valid, so this equation should be valid for all the time. That means, so this equation should also be valid when t is 0 plus. So that means, so dIL over dt when t is 0 plus, it is also valid. So it is equal to A1 times minus 2. So when t is 0, so e to the power of 0 is 1, so plus A2 times minus 5, so e to the power of 0 is 1, so e times 1 plus 0. So we can just remove these two terms. Okay, so this is the second equation. So we should find out, okay, dIL over dt at post 0 time from initial condition. So let's look at our circuit again. So let's go back to the very beginning. Yes, let's go back to here. So when t is larger than 0, so what is dIL over dt at post 0 time? So how do we find out this? So we can always use the inductor differential equation. So we can always use L dIL over dt is equal to VL. So this is also valid when t is 0 plus. So from here, so we can solve for di over dt at post 0 time is equal to VL 0 plus divided by L. So how do we find out VL? So we can use the Kirchhoff voltage law. So if we want to find out VL, so we can look at this loop. So basically you see here, so VL voltage is equal to VC voltage minus V. So V is 6 ohm, the voltage of the 6 ohm resistor. So that means, So VL voltage at 0 plus is equal to VC voltage minus V, which is 6 times IL. So at 0 plus time, so 0 plus, so here is 0 plus, so it is, so for VC 0 plus, so let's look at here, the initial condition is 0 minus, so 6 times IL 0 plus, IL 0 plus is also 0, so it is 0. So that means, so VL is 0 divided by L, L is 1 Henry, so this is 0. That means DI over DT at 0 plus time, DIL over DT at 0 plus time is 0. So this is 0. So our second condition here, it is 0. So that means we have equation 2. So if we solve equation 1 and equation 2, so let me write it here. So solve equation 1, so it is A1 plus A2 plus 1.6 is equal to 0. So the second equation is A1 times minus 2 plus A2 times minus 5 is equal to 0. So we can solve for it. So I write directly the solution, but you can verify that it's simple. So A1 is equal to 1 is minus 8 over 3. A2 is equal to 16 over 15. So if we know A1 and A2, so we can find out the final total solution from here. So we can write IL is equal to A1 times E to the power of 2t. So A1 is minus 8 over 3 E to the power of minus 2t plus A2 times E minus 5t. So plus A2 times E minus 5t plus the steady state solution 1.6. Okay, so finally we find out the inductor current when t is larger than 0. But the question asks for original question asks for the resistor voltage of the 6 ohm resistor voltage, and also it asks for the resistor current, the 4 ohm resistor current I and V. Okay, so first, so V is simple because, so if we know the inductor current IL, so we can calculate easily. We can use 6 ohm times IL because this inductor current flows through the 6 ohm resistor. So we can use, so V, the 6 ohm resistor voltage is equal to 6 ohm times IL. It gives us, say, 6 times minus 8 over 3 E minus 2t plus 16 over 15 E minus 5t plus 1.6. So we can solve for it. It's simple. So let's look at I. How do we solve for I? So I is equal to VC, because so the capacitor is in parallel with this 4 ohm resistor. So I is equal to VC divided by 4 ohm. So how do we solve for VC? So VC, if we apply KVL, so VC, the voltage from here to here is equal to the voltage if I follow the current direction. If I define an imaginary current, a loop current that flow from here to here, so VC is equal to VL plus V. So we can write VC is equal to VL plus V. So it is equal to L DIL over dt plus V. So because L is 1 Henry, so L is 1 Henry, so it is equal to L DIL over dt plus V. V is equal to 6 times IL, 6 times IL. So because we know IL, so we can calculate VC easily. So VC is so DIL over dt. So let's take the derivative of IL. So it is minus 8 over 3 e minus 2t times minus 2 plus 16 over 15 times minus 5 e to the power of minus 5t. 1.6, take the derivative of t is 0 plus v. So we have the formulation for v. So it is 6 times minus 8 over 3e minus 2t plus 16 over 15 e minus 5t plus 1.6. So this formulation is quite long, but definitely we can simplify it. So now if we calculate IT, so look at here. So I of t is equal to VC divided by 4 ohm. So VC divided by 4 ohm. So because we know VC, so we know VC from here, so we can easily calculate I of t. So we can easily calculate. This completes our solution. Thank you so much for watching the video. Hopefully you can practice more for second order circuit. Thank you. Bye bye.